Now we're going to look at the mean value theorem. And the mean value theorem really comes as a consequence of Rolle's theorem. Rolle's theorem was, I believe, discovered first, and then you can use Rolle's theorem to help you prove the mean value theorem. But anyway, the mean value theorem says the following. Let f be a function with the intervals that f with the following conditions, that f is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So those are the same as the first two conditions of Rolle's theorem. But we leave out the third condition. And the conclusion is different. What the conclusion says is there is some number c on the interval from a to b, the open interval, where f prime of c isn't necessarily 0, but it's equal to f of b minus f of a over b minus a. Now, we have talked about these two things before. Remember, this was the definition of the average rate of change in a function on an interval, and this was the instantaneous rate of change in a function at a point. This was also the slope of a secant line, and this was the slope of a tangent line. So what this is saying is that if both of these two conditions are met, then if you draw the secant line, let's look at this example. Here's a function which is supposed to be continuous and differentiable on the interval from a to b, continuous on the closed interval, differentiable on the open interval. Now, what I've done here is I've taken the point on the graph that corresponds to x equals a and the point that corresponds to x equals b, and I've just drawn the secant line. And so the slope of that secant line is the f of b minus f of a over b minus a. So what the mean value theorem says is that in the event that those two conditions are met, that there is a place where a number c, where the slope of the tangent line is equal to the slope of the secant line. And here is the way that I think of it. What I do is I'm going to take this sheet of paper and I'm going to try to line it up with that secant line. Now what I'm going to do is I'm going to pull my paper away from that secant line, but I'm going to try to keep it parallel to that secant line. And the last point that is uncovered is the value of c. I missed it a little bit, but I hope you can see what I'm getting at. Alright, so check this function to see whether the conditions of the mean value theorem are met, and if they are, find the value of c. So is the function continuous? Is it differentiable? It's a polynomial. It's continuous everywhere. So it's continuous on whatever interval it is, 0 to 1. Is it differentiable? Well, f prime of x is, looks like it's 3x squared plus 2. That's never undefined, so it's differentiable everywhere, but in particular it's differentiable on the open interval. So is there a place where the, those are the only two conditions we have to meet. So we need to figure out what f of b minus f of a over b minus a is. So that would be f of 1 minus f of 0 over 1 minus 0. What is f of 1? F of 1 looks like it is 1 plus 2 is 3 plus 1 is 4. and f of 0 is 1, and then that's 1, so it looks like it's 3. So the slope of the secant line is 3. So according to the mean value theorem, there's some place where the slope of the tangent line is also 3. Well, that's how we find the slope of the tangent line. So what we need to do is set this slope of the tangent line equal to the slope of the secant line and solve for x. So we get 3x squared plus 2 equals 3. Subtract off 2. 3x squared equals, 1? X squared equals 1/3. So x equals 1 over the square root of 3 plus or minus, but we want the one on the interval from 0 to 1. So it must be that one. Alright, let's look at number 2. Same instructions. Check to see whether the conditions of the mean value theorem are met. And if they are, find the value of c guaranteed. Alright, so we're looking at 1 over x on the interval from -1 to +1. I guess that should be a closed interval. Are the conditions of the mean value theorem met? No, they aren't. The function's not continuous at x equals 0. So condition 1 does not hold. Theorem does not apply. THEOREM does not apply. And finally, one more example. Let's get rid of that unnecessary word. You leave for Nashville at 1 p.m. An hour later, you arrive having driven 63 miles. Was your instantaneous velocity ever 63 miles per hour? So, alright, so the average the average velocity was 63 miles per hour. Very likely, at some point you went faster than that, and at some point you went slower than that. But the question is, was your instantaneous velocity ever 63 miles per hour? And how do you find the instantaneous velocity? Well, you look down at the speedometer. Are you guaranteed that the instantaneous velocity was ever 63 miles per hour? Well, if you think of f as the position function, then, and let's see, b is maybe 1 and a is 0, or a is 0 and b is 1, then this is, the right side of this equation is the average velocity, and so that's 63. And then f prime is equal to the instantaneous velocity. So this looks like a mean value theorem problem. So basically we have to decide, does the mean value theorem hold? Alright, so here f is the position function. Is your position function continuous, assuming your position is a function of time? Well, let's think about that. Here's time t. Here's the position. What would it mean if your position function looked like that? It would mean that you disappeared for a while. Or what if it were something like this? It would mean that you instantaneously transported. I suppose that's possible, but not likely. So condition 1 seems to be met, that your position function is continuous. And the second condition is f differentiable on the open interval from a to b? Well, what it's asking is, does the derivative exist? Well, what is the derivative? The derivative is your instantaneous velocity. Do you have an instantaneous velocity all the time during that hour? even if it's zero, that's okay. I think you do. I think if you look down at the speedometer, you can find your instantaneous velocity. So it looks like both conditions of the mean value theorem are met. Therefore, the conclusion is valid, and there is a place where the velocity, the instantaneous velocity, is equal to the average velocity.